Hello there. Welcome to CERN, the European Laboratory for Particle Physics. We're here at the ATLAS experiment on the Large Hadron Collider at CERN. My name is Stephen Goldfarb and I am a physicist on the ATLAS experiment. And this is my colleague, Kylie.
Hi, my name is Kylie Kennedy and I'm a PhD student on the ATLAS experiment at Columbia University.
So we're going to be your guides today. We're going to take you on a visit. You're going to get to go not just out here at point 1, the point where particles collide below our feet, but we're actually going to go down underground and see the ATLAS experiment, and that's where we collect all the data from the LHC collisions. You want to come with us? Put on your mask. You can't come down unless you got your mask on. We're going to get you a helmet when we get inside, so come along with us. All right, so everybody, we're all going to put our helmets on because we're going to go underground. We're going to be almost 100 meters underground. That's where the Large Hadron Collider collides protons together in our detector. Kylie, lead the way. Kylie's going to head on through our personal access device, or pad, and it's going to check to make sure that she is who she says she is. It's going to check her eyes here with the iris scanner. Hey, it worked. All right, we're all going to go through. I'm going to go in through next. It is not a shrinking device. The detector really is big. You'll see.
Thank you.
Okay, everybody ready? You got your helmets on? We're going to push the button and call the elevator up. It's only 2 floors down, but 2 floors down is more than 90 meters. Let me show you where we're going to go. If you take a look over here, you can see what our beautiful little detector looks like. This is wrong. It's 46 meters. I know, I've seen it. It's a long distance from one end to the other. It's a very, very large detector. The whole point is that we surround the collision point. The protons come in here and they collide in the center of that detector. And we produce little people. No, we don't produce little people. These are physicists. That's the actual size of the people who are down there. And so we might see some people now. The LHC is not in operation. Don't worry about that. There are no collisions. We're all working on our detectors. This is a long shutdown. All of the different experiments are working on their detectors, and the people who give us beam, the LHC engineers and scientists, are working to give us better beam with more collisions per second in another year and a half. We're going to have that. Okay, let's go down. Take us down. We're going to go all the way down to the bottom. -2. Only 2 floors, like I said, but that first step is a big one.
But if you look right here, you can see this number here shows how many meters below the surface of the ground we are. You can see how rapidly down we're moving to access the detector cavern.
We go underground basically because we couldn't afford the land above ground, right? But the whole accelerator, which is 27 kilometers around, is all buried underground. There are 4 places on the Large Hadron Collider where the protons collide. We surround them with detectors. We're at ATLAS, point 1 of the LHC. There are 3 other experiments. If we go around that way, there's the ALICE experiment. Other direction, there's CMS, and over there's LHCb. They're all very, very important, very beautiful experiments with thousands of people working in collaborations on the experiments. We've made it. We're down at the bottom. One more time, we're going to go through. Kylie, do you want to go
Sure.
first? Just to make sure we didn't change into some other types of people on the elevator ride.
Thank you.
Hey, it worked. She didn't turn into Superwoman either. There we go. My turn. See you inside.
Thank you. You have been identified.
Come on in. Okay, we're going to take you inside where you can see the detector. Now here's the thing. You're gonna see an enormous device and you're not even gonna see the whole of it. You're gonna see parts at a time. We have this entire huge device we're gonna take you to see, and it's designed to look at the absolute smallest things that exist in our universe. In fact, can't even say large or small, can we? They're fundamental particles that we're looking at, which have no volume at all, right?
That we know of.
That we know.
That we know of.
We'll always measure that.
In fact, when we refer to the size of particles, we're not actually referring to the volume that particles take up. We're actually referring to the masses of particles, which we can actually measure more precisely, because of course the volume of particles is something we really don't quite know about. And if we did know the volume of particles, it would unlock a lot of key mysteries.
Well, I think it would then mean that they're not fundamental, probably.
Yeah, it could
right?
be.
Heisenberg, I don't know, says that we're never really going to know, right?
Mm-hmm.
We can never tell exactly when the size is of a particle.
Yeah.
We can't tell its position exactly if we know how much it's moving, and we can't tell how much it's moving if we know its position. It's a strange world, but we're going to take you to see a little bit of that world now. There is a whole lot of scaffolding. That is not a detector, but this is what's holding up everything. We're going to take and walk you all the way upstairs. I hope that you're in good shape. I hope I'm in good shape. Yeah, I know Kylie's in good shape. We're going to go all the way upstairs and we're going to take a look from the top of the detector so you can have a view over everything. And then we're going to try to give you some more views from the inside. Here you don't see anything. Come on up. So we're at the far end of the experiment. These are called, this is the muon spectrometer. These are tubes filled with gas and a wire in between. When a charged particle goes through this, it leaves a trace.
It ionizes the gas.
Exactly, it ionizes the gas and sends a charge, which we read out with the electronics. We have to connect the dots to see the track of the particle that goes through. What's really cool here, what I really like, if you take a look here, that's the LHC. See the blue there? If you go underneath that, you're under the LHC. That's something.
Yeah.
Yeah. Okay.
I was going to add about the beam shielding.
Oh yeah, you surround it. Yeah.
So the actual tube that the protons go in when they're traveling through the LHC is only about this big. But if you look here, you see what Stephen is touching right now. That huge object is beam shielding that surrounds these tiny proton-proton beams, because as the protons are moving around in a circle, they're accelerating because their direction is changing. And so they emit showers of particles by this kind of circular acceleration. And close to the detectors, we don't want that stray radiation to interfere with the measurements we're trying to obtain from the proton-proton collisions. So we have this massive, massive beam shielding that you can see is probably a couple meters across itself. So.
Okay, you guys go on. I'm gonna hold up the LHC, all right? I'm just gonna keep this up. I got it. Don't worry about it. There, we made it. The top of the Atlas experiment at the LHC. I'm so glad that you could make it all the way up here with us. I'm glad you've got your dosimeter on, like we've got our dosimeters on, and you've got your mask, and you got your helmet. And now, let me answer this one question that you seem to keep asking, is like, why? Why are we doing all this? Why did we build such an enormous device? Why did thousands of people from all over the globe come together to do this? This is no easy task. Why did they all go to their funding agencies and ask for resources to do this? And why do human beings say, yes, absolutely, this is something to do? It's fundamental research. Maybe there are some questions that you could answer or maybe ask that we're trying to seek the answers to here.
Yeah, so I think the fundamental question that us as physicists are interested in is why are we here? Why is the universe the way that it is? And what are we made out of? And so these kind of questions go back all the way to the beginning of the universe, to the origin of the universe, the Big Bang. And so right after the Big Bang, all of the stars in our galaxy and all of the galaxies in the universe were compressed into a tiny volume. And everything, as you can kind of imagine, was super, super dense and super energetic. And so the types of physics interactions and processes were very different back then than they are today. And so we need a specialized system to try to study those early interactions of that very hot and dense universe. And so the way that we've approached this way to study these particles is by simulating, so kind of trying to recreate the conditions of the universe right after the Big Bang. And that's by colliding these protons at these really, really high energies to try to recreate that high energy universe. And so you can see here, if we look down into the detector, you can see kind of through all of these different highly complex layers of the detector is the actual interaction point where we see those two protons come together and collide. And we have a myriad of various layers of the detector that perform different measurements so that when we put it all together, we can identify the kinds of particles and their energies that emerge from these high energy collisions to better study what's actually happening.
I mean, just to be fair, before doing all of this, Kylie came to me and said, look, you were around 13.8 billion years ago. What was it like back then? But I just don't remember. So that's one of the reasons we have to reconstruct it. Actually, our field really started because we saw that there were these particles we couldn't understand that were kind of messengers from the Big Bang hitting us over the head. There's cosmic particles that come through us all of the time. What we found out from them is that there's a lot more out there than what we're made out of. Ourselves, I don't know about Kylie, but I'm made up of up quarks and down quarks and electrons, and I think she is too. That's what makes up pretty much all of the matter that we know, because those are stable particles. But if you add energy, you can actually create mass, right? E equals mc squared. That's what goes on down here. We take light particles, stable particles, we add a lot of energy, and then in the collisions, we can produce more massive particles. The E becomes mc squared. Those particles can then transform to the lighter particles, and we get E again. The mc squared goes back to E. We have to reconstruct all that, and we learn about these particles that existed in early time, and which can be produced by interactions out in space as well. This tells us about the basic fundamental building blocks of our universe. That's what we care about. Fundamental particles, particles that aren't made up of other particles. We think we have a pretty good model now. We're pretty happy with it. We can put it all on a coffee cup even. We have the particles, and we have on the other side of the coffee cup an equation that explains how they interact. We're kind of happy, except that's about, what, 5% of the universe that we understand. There's a lot of other stuff out there.
Exactly.
We're missing. What are we missing? We're missing stuff, right?
So I think we can do a lot of things very well, and I just want to point that out. What we call the standard model of particle physics, which was developed in the 1970s, and which, since its development, piece by piece, particle by particle, we've discovered every single particle predicted by this physics model in the 70s. It's one of the most precise, if not the most precise, model in science that has ever been created by humanity, that we know of. However, as Steve just pointed out, it only describes 5% of our physical universe. And so we know there is so much more out there that we need to study to really understand the fundamental nature and the fundamental building blocks of our universe. And that's something we're trying to do here. So physicists are looking to study extensions of the standard model. So the standard model, we know it can't be the only be-all and end-all physics model. So people are looking to add particles to the standard model to explain various kind of questionable phenomena that we have observed so far. One of those being dark matter. So dark matter is about 20 to 25% of our universe, and astronomers and astrophysicists have measured this, except we don't yet know what particle or set of particles is responsible for our observations of dark matter, and we have good reason to think it is indeed a physical form of matter. And so that's one of many things that we are trying to create here at the LHC in conjunction with thousands of other scientists and other collaborations and theorists and phenomenologists who also are interested in studying dark matter. And that's just one topic of many.
Then the other dark thing that we're missing, it's great because our great-grandchildren are going to laugh at the fact that we call these things dark just because we didn't know what they are. But that's why science is so fascinating. We're looking for stuff we don't understand yet. The other thing that's dark, we call dark energy. That's most of the universe, right? That's whatever energy is out there that's making us expand faster and faster. Now, my wife tells me all the time that I'm expanding faster and faster myself, but that's not the same thing. The universe itself is growing and going at a faster and faster rate. We don't get that, and a lot of people don't get that. It's not clear particle physics will answer that. Could take other forms of physics. Could be astronomy will give us some answers, astrophysics, we don't know. But we have a lot of big questions, and we're going to try to answer them. And that's why we're continuing. We're upgrading this. We're upgrading the LHC. We're going to do that again later on. It's all planned. And then we're going to look to do something even higher energy because that's what we have to do. We're human beings. We're curious. We got to find the answers.